fractions. All right, good job. So now that we have addressed exponent rules.
Yes.
Yes, sir.
What are you trying to do?
I'm just debating whether I like myself slightly to this side. Sorry, this side.
Now this is going to be a fun episode.
Okay.
He's got to burn time.
All right.
Hey Gary, what's the date? It's the 3rd, right?
It's the 3rd
Okay, sorry.
of February.
Exponential functions, right? So we have been talking about exponent rules, right? What are all the rules that we use with exponents? We've been talking about those and how you solve those and simplify them, right? Well, now we're going to actually talk about equations. When I say functions, I'm actually talking equations. And we haven't really talked about functions yet in terms of what functions are. I will be discussing that. Do I want to discuss that right now? I don't think so. Just it's basically some things are functions and some things aren't. If they're not, doesn't mean they don't exist or whatever. It just means they're not a function, right? And so don't worry about it. For now, just think of when I say function, it is definitely an equation when I say a function, okay? But we're going to talk about exponential functions, and we're going to look at how they look graphically, because a picture is worth 1,000 words, right? And so a lot of times, you'll see an equation and think, well, what does this have to do with anything? It doesn't make any sense. I'm confused, right? Well, when you start to see the graph, it starts to make a pictorial sense that you can say, oh, I get it. I get what exponential growth is. When they say something is growing exponentially, I get what they mean. It's not a straight line, right? It's not a straight line that just keeps going and it kind of grows steadily with a slope, rise over run, rise over run, rise over run. It's not a steady growth like that. It is actually an exponential growth. And so you're going to see what that looks like. So we're going to take I'm going to put an equation up here, and we're going to actually use a T-chart, and we're going to graph it so we can see what it looks like, okay? And in graphing it, we're going to have to use our exponent rules that we have learned, okay? So let's say I gave you this equation. Y is equal to, what if I did 3 parentheses 2x to the x power? So suddenly I'm actually using the exponent as the variable, okay? This is the first time we've done that, right? First time we've done that. The first time. Yes. All right. So we've got x and y.
Oh, I hope this doesn't have content protection.
It doesn't have what?
Content protection.
Oh yeah, don't worry.
Sorry, Gary, may it just cost you like $500.
All right. So we're gonna choose some values for. Yeah, let's choose some negative values for x. Let's say x is -2. Let's say x is -1. Let's say x is 0. Let's say x is 1. And let's say x is 2. And let's sort of see what our y values are when we do this, when we plug those in. So suddenly, this one means I'm going to have 3 times 2 to the -2. Now remember, negative exponent does not mean the value is negative, right? It means whatever is negative exponent goes downstairs into the denominator, right? That's all it means. So what would this be? Technically, if I wrote this, I'll just do it over here for a second. So 3 times 2 to the -2. How could I simplify that using my exponent rules? Mira.
You're gonna take the exponent and put it below.
All right, so I could do this, right? I could create a fraction, right? And then I could take only what the exponent affects and move it downstairs. Is it okay to say 3 times 2 is 6 and then raise it to the?
PEMDAS.
No. PEMDAS says exponents before multiply, right? You can't multiply first. You've got to do your exponents first. So I've got to deal with this -2 exponent to that 2 only. And like Mira said, I'm going to bring it downstairs. So suddenly I have 3 over what?
4.
2 squared, which is 3 over 4. Okay, so that is 3/4. Everybody agree with me? All right,
Oh, yeah.
does that make sense?
Yeah.
Wait, Gary, I thought you said that it wouldn't be a rise of a run thing.
It
Well,
is-
you'll see. Yeah, you'll see what I mean in a minute. Just give me a few minutes to do that.
So
well,
basically, it's
Because
like
is it because you see the fraction and so
Yeah.
you're thinking rise over run?
Yeah, because you
Yeah.
said every
Well,
time you see a
that's a
fraction
wide
when we're using a graph, it's at rise of a run.
Right.
So-
But see, what we're not solving for m. Remember in that
oh,
in
yeah.
that
Oh, yeah.
right? It's y equals mx plus b. M would be a fraction, right?
Yeah.
M is your slope. This is not. This is your y. When x is -2, y is 3/4. It's less than 1. Does that make sense?
Yeah.
Right? And then, okay, so let's try -1. So we've got 3 times 2 to the -1. So that equals, I'll bring this downstairs, right? So 3 over 2 to the +1, which is just 2.
Yeah.
Everybody agree with me?
Yeah.
3 over 2.
0 would be 3.
Or when,
And 0.
would you make that into
Because
a proper fraction?
it's 1 and then 3 times 1 is
Yeah.
3.
3 times 2 to the 0 power. 2 to the 0 is 1. So 3 times 1
3.
is 3.
Hey
So we
Gary,
got 3. Yes.
would the first or would -1 would you have to where it's 3 over 2? Would you have to turn that into a mixed number so it's actually a proper fraction,
No.
or would you just leave it as an improper?
It's actually okay either way.
Improper
When you
fractions.
graph it, you may need to think of what does that mean in a mixed number. I think it's a good question. I think I'm going to put equals 1.5. Don't you agree with me? Because that might help me when I'm graphing. Because otherwise, 3/2, what is that? Where is that on the graph, right? So, okay. And then 1. Okay, so suddenly that's what? 3 times 2 to
That'd
the
be
1
6.
power. So that's 3 times 2, right? 3 times 2, which is equal to 6, right? There we go. And then 2. 3 times 2 squared is 3 times 4, which is 12. Wow, it's starting to go up there fast, right?
It doubles.
Okay. So now can I erase this part?
Oh, everything is multiplied by 2.
Yeah, it doubles.
3 times 2 is 6.
I-
6
I-
times
I
2 is
just-
12.
3/4
Interesting, yeah,
times
interesting.
2 equals
Alright,
negative
Good
6.
notice. Good thing. Good
Observation.
observation. That's the word I was looking
As
for.
I
Good
told
notice.
Michael,
Good
Good.
notice.
as I
Good
told Michael, I
observation.
noticed
Okay.
these things.
So now, what do we have? We've got
Good notice.
Why'd you change your chair again? Right to back.
What?
is that on here? Okay, good.
I think so.
All right, so
What is
we're gonna have.
I think it's a graph.
Yeah, it's in
So
Could be a
when
cake.
when you're graphing these guys, you have to look at all your x-axis, all your x values, and then you have to look at all your y values, right? And I notice my y values start near 0, or at least below 1, and they go all the way up to 12. So I'm going to have 12. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. And then I'll just 1, 2, 3, 4, whatever. Right? So I think that's all we're going to need because there's no negative y's, so I don't really need to have any lines down here, right? I'm never going to go down to negative the way it looks right now. So let's start plotting it. So the first coordinate is
It's
-2, 3/4. So -2, 3/4. So 3/4 is just a little less than 1, right? Does that look about right?
Yes.
And then -1, 1 and 1/2. So -1, +1 and 1/2, that's about right there. Right?
No, it's
Oh, wait.
higher up.
What am I
It's
doing?
above 1.
Wait, Gary,
What am I
why is
Yes, 1 and 1/2.
Yep.
I was just testing you guys.
Totally, Gary.
All of a
Gary,
sudden,
why
this is going the wrong way
Gary, why is 3/4 in the negative?
because it said when x is -2, I have to go. This is a coordinate.
Oh,
This is -2, 3/4,
I
right?
am a smart.
So -2 up 3/4. That's a good question. It's a little confusing, but once you realize these are coordinate points, right? And I don't take the time to write them in parentheses, but they are. That's what they are, right? That's what a T-chart does. It gives you a bunch of coordinate points that you can then graph. So we just did this one, and then 0, 3. So 0 means I don't go anywhere left to right, but I go up 3. 1, 2, 3, put a dot, right? All right, and then the next one is 1, 6. So I go over to 1, and I go up 6. 1, 2, 3, 4, 5, 6. Ooh, it's starting to climb kind of fast. This is interesting. And then 2, 12. Holy smokes. 2. And then all the way up this way. I happen to know that's 12 because I counted earlier. So, wow, that's interesting. So if I were going to graph, if I was going to draw this graph,
It would have curves.
It's a wee graph.
Careful with the line.
There is no line
So
here.
beautiful.
It's a Gary line curve. It's a parabola. Oh my God.
It's a parabola.
no, this is not a parabola.
Parabola is when it's a U.
A parabola would be like a U where it actually starts getting higher again, right? Now notice this is getting smaller and smaller and smaller and smaller. Whoops, sorry. And smaller and smaller and smaller. Will this ever hit 0?
No.
No.
Yes.
Yes.
No.
Sure.
No.
Yes.
Sure.
It will.
I mean, like,
No,
Because it's-
it won't. You're right. For whoever said no,
Me.
right? Yes.
Oh, zero.
It goes
yeah,
forever.
zeros to the right.
It goes
so-
forever and ever, getting closer and closer to 0. So if that, you know that there's this story where I can't remember I'm gonna make it up sort of. But like if I want to walk, towards that door, and
Yeah.
each move I make is half of the distance from here to the door, right? I would go half, right? Boom. And then I'd go half again. Boom. And then I go half again. And then I go half again. And then I go half again. And then I go half
Wait, Gary.
again. Will I ever reach the door?
Yes.
Yes.
No.
No.
Because I'm always going half the distance to the door, right? I'll never hit the door.
Wait, Gary. If you're going half
Isn't
the
that
distance
weird?
to the door, isn't a half 1/2?
Yes.
Well, since
Then
you
how can you have multiple halves?
Look.
You can only have two
okay,
halves.
Okay.
Half
Say this
of
is 3
half.
yards to the door.
If it's
Gary can only walk 1.5 yards.
If there is
When he gets there, he can only walk half of
if
that.
there is a
Right.
chunk
When he
of
gets
half,
there, he can only walk half of that.
I mean, I'm
There
just
we go.
curious. If there's only two halves, how can you have multiple halves?
no, because there's a new. You start again each time.
But wait, then when
So
did
like-
you get to the
so,
door
okay,
then?
okay. So
Confused.
this is on the
I am
video.
confused.
So if it's 10 feet to the door, my first move is that I can go half of that 10 feet, which is 5 feet. So I go 5 feet, right? Boom. Okay, now I'm 5 feet to the door. My next move is half of that distance from 5 feet.
Oh,
So I can go 2.5 feet.
okay.
My next move is half of 2.5 feet, which is 1.25, right? And then my next move is half of 1.25, right?
Okay.
But I'm always getting, my moves get smaller and smaller, and I'm never reaching the door. That's kind of a sort of a, more theoretical idea.
But since every time you're still making at least a little bit of progress, technically at that times infinity, eventually you would have to reach the door.
That's what you would think, right?
But
And it's a
half of
paradox. It's a
zero, zero,
paradox. I'm not
zero,
actually
zero,
sure.
zero, zero,
I agree with you.
You would.
15.
But isn't there always going to be space between you and the
So
door?
on a molecular level, you aren't even touching the floor, so you wouldn't actually reach the door.
But for us, the molecular level is tiny, right? But to a molecule, the molecular level is huge, right? Or to a proton or a quark, the the size of a molecule is like
We should really get back to the
humongous,
video.
right?
Gary, we should really
suddenly-
get back to the video.
Right, okay, yeah, whatever.
Gary,
All right, so this is the graph. Guys in the back table, please. This is a graph of showing exponential growth. So notice the graph goes on forever to the left, getting closer and closer to 0, but never really touching, right? And to the y, it gets further and further and further away, and it will continue to expand. It goes on through infinity this way. Does that make sense? That make sense? So the x, if I went to infinity on x, or like 1 billion trillion zillion billion Google billion, right? Then I'm still gonna eventually, if I go high enough, I'll find a y, but it'll be really high, right? Right? Really, really high. Yes, Ben.
Well, what would that line be called?
What line?
The curved line. Is it just a line?
It's that's a good question. I'm gonna have to say I'm not quite sure.
Let's just call it an EF.
On the video, I can't believe. Okay, but anyway, this is an x. Just consider it an exponential growth curve, right?
For now, let's just call it an
Basically.
EF line.
The what?
An EF line.
Okay, sure. Okay, but
For now.
but this is the way compound interest works. You start out with $1,000. You put it in the bank, right? Or you put it in something, and you're making compound interest, right? Well, the first year you don't make very much. Say you're making 5%, right? That's a lot for nowadays in the bank, But let's just say you did. So you make 5% in a year. So 5% of 1,000, what's that?
1,000 divided by 5. That's...
I think that I realized, like, if you had 1,000 in the bank, then you took out 500, and then you kept doing that, then you still have a tiny, tiny cent between. It makes sense now.
Oh, the light bulb just went off.
That's-
It's 20.
But now we're gonna go the other direction. Okay, so Andrea, now we're gonna go the other direction. Instead of getting smaller and smaller, right? We're actually gonna get bigger and bigger. And you guys actually notice that, look, what does the y do
It doubles.
as you move one value up on the
It
x?
doubles.
The y is doubling every time, right? So suddenly, in the beginning, I'm making, 5% on 1,000. What's that? 5%. 1,000 times 0.5. So what would that? Well, but how could you think of that? 5%. What? Yeah. So it'd be 0.05, and if you multiplied that out, you'd end up having 5,000. And you're going to bring it over twice, it'd be $50. So at the end of the first year, you have $50, right? So the next year, though, at the end of the next year, your principal was $2,050, right? And so you made just a little bit more interest, right? And then the next year, you made just a little bit more interest. And the next year, you made just a little bit more interest. And then after 5 years, you made a little bit more interest. And 10 years, it's when you get to like 30 years that suddenly, look, in 1 year, you went from 6 to 12, right? Like it starts to grow exponentially. And eventually, your investments become gigantic. Way more value. Now, this is really important. In fact, on the bottom of the homework, well, go ahead. Ask your question first, and I'll say this.
Questions.
Yes.
One is, wouldn't that make the amount smaller, or are you adding that?
Oh, I'm adding that. Basically, when you have money in a bank, you earn interest, and so if it's 5% of 1,000 in a year, you will have made $50, right?
Wait, do you take some of your money?
No, you make money. Oh, it's a certain.
You make-
Making $50. So
The bank
keeping your money in the bank.
the bank pays you to keep money in the bank.
because you're paying the bank.
Not much.
Wait, then why aren't they giving me any money?
'Cause-
Rude.
Well,
Because
that's
you're
just,
too
it's got to
young.
be, there's two different kinds of account, there's a few different accounts, but there's a
Debit card.
checking account
That's
and there's a
not-
savings account. If you have it in a savings account, it's an interest-bearing account. But it won't be 5%. It's going to be more like 1% or 0.5% or
You're gonna make like
crazy.
a penny a year.
Yeah, right.
Whoa,
So it's going to take a
rich.
long time.
Penny?
In a typical savings account,
Yeah.
it's going to take a long time. I mean, we're talking like 100 years before your money's really starting to, go somewhere. But
Oh, you think that?
but-
Oh, no, like it's paying.
so, guys, so that's the whole thing about investments, right? Is you're looking for things that give you the safest but largest amount of growth per year, right? You can find investments that'll give you 100% growth in a year. The only thing is it's going to be really risky,
I
right?
was gonna say, tell me which investment it is, Gary. I'm gonna do it.
You know, you can find them which will do more than that in a
Last
year.
we bought
But they will.
GameStop.
You what? Oh yeah.
$1 million.
Right. So you guys experienced that last year with the stocks with Matt. That's awesome. Yes.
And my second question was, if you changed the 2 that's inside the parentheses to 3, would it grow 3 times the amount every time?
Let's try it. Let's try it. Okay. Let's see. But does that make sense to you guys? You see how this is working? That over time, so with finances, this X value is time, right? And the Y value is money, right? And you know, your money starts to grow after enough time. So, for example, we're going to talk about this more as you know, in a future time frame. But we're going to talk about compound interest exactly and how that works and what's the formula for compound interest and you know how that could be valuable to you guys. Compound interest is way more valuable to you than it is to me. Does anybody know why? Way more valuable. I mean, it is like unbelievably valuable to you right now. Why? Because you have a lot of time in your life. I have less time, right? I mean, what am I? I'm almost 60. I can't believe it. Jeez Louise. But 57, I don't even know what I am. I'm either 57, 58. I've forgotten. But it doesn't matter. But the point is, that like if I'm 60, let's say I live to 100, I only got 40 years. How many years do you guys have? You've got like 100 years, right? If you live to 100, if you get 90, yeah, you have a lot that you could do. If you started with, guys, if you started with, say, $1,000, like somebody donates, gives you $1,000, and you put it in the bank, and every month you put in $30. That's it. Every month for the next, 30, 40, 50 years, you will easily be a millionaire. Easily. $30. How many people are going to have $30 in a month to put in there? Everybody.
No.
The number of people that spend, I mean, I don't know very many people that spend less than $30 eating out every month.
My
Right? Go ahead.
If you have a good job, then that's more than you make for an hour.
Oh,
Right.
You should
Make 60
it's
per
10%. You're supposed
Yeah.
to put 10%
Well, time
of
in.
the money you make
Oh,
into savings every month.
Right. That's a great rule of thumb. That's awesome. That is a great rule of thumb.
Oh yeah, I could just.
We could talk about all this stuff. Finances. We can talk about finances as we get closer. But let's just now let's focus on the exponential growth graph, right? The function, the exponential function graph. So we'll actually let's leave that one up. Let's do another one right here. So you said, Ben, you were saying y is equal to
3 and then parentheses
3 to the x, right? All right, so now we're going to see what this does to the thing. Let's go x and y. To be honest with you, I don't know the answer, so I'm curious. I want to know. So let's do the same thing. We'll do -2, -1, 0, 1, and 2. All right, so we have 3. Okay, this is going to be 3 to the -2. That'll be underneath. 3 to the 2 now, and then 3 up above, right? You see what I did?
Yeah.
I basically brought that down and put the
You won by
made it
30.
positive. So it's
It's 1/3.
3/9, which is 1/3, right?
Oh, yeah.
So that's going to be 1/3. That's interesting. Okay, so now -1. So that's going to be 3 over 3 to the 1. That's going to be 1, right? All right.
Yeah, it is.
That looks like times 3, doesn't
Yep.
it? That's interesting. And then if it's 0, 3 to the 0 is 1. 3 times 1 is 1. I mean,
Nope.
3, Gary.
I was just checking to see if you were right.
Yes.
Sure you were.
Sure I was. Okay,
Yes, he
so
was.
then we
I
got
believe that.
3 to the 1 is 3, times 3 is 9. All right, 3 to the 2 is 9 times 3 is 27.
27. Woo, it
Holy
does.
smokes. So
Graph it.
let's graph it on the same thing. This is 12.
We need to go to
13,
27.
14, 15, 16, 17. Uh-oh. 18, 19, 20, 21,
21.
22, 23, 24, 25, 26, 27. Ah! We did it.
Only
Okay.
barely though.
So -2 1/3. -2 1/3. That's about right here, right? Here, I'll use a different color because it gets complicated if you don't. All right, so we got -2 1/3, right about there. And then we have -1 1. -1 1. Ooh. Already, that seems like it's going pretty fast. 0 3. Oh, that's interesting. Look at that.
Whoa,
0 3. So that's going to be there, right? 1 9 1. That was 6 7 8 9. And then 2 27. So 2 27. Right? So suddenly
I want that life.
I've
in a
got
week.
this unbelievably tiny.
It's such a big growth.
It grows exponentially.
Oh my god.
Right?
Did a Gary line.
It's growing exponentially.
It's like
So-
straight curve. Straight.
So yes. So the homework tonight is going to be graphing these, right?
Did you stop the video?
And
Gary didn't stop the
wait, I'm not going to finish. I'm not going to stop the video yet. On the bottom of this, I put something. I said the value. It's a quote by Robert Kiyosaki. Robert Kiyosaki is a very well-known contemporary businessman. He's known for writing a book called Rich Dad Poor Dad. Did you guys study this at all last year? Rich Dad Poor Dad. He started out when his biological father was poor, and then eventually poor. I shouldn't say poor, but that's what he calls it, because he just basically worked a steady job, and he basically worked an hourly rate, and he didn't make a ton of money. Hi guys, we're talking about exponential functions and exponential growth, right? And I'm sort of comparing this. This is the graph of exponential growth, and we're just looking at how this relates to money as well, because that's very common. When people talk about compound interest, this is what happens. And I was telling them that they have an incredible advantage over us because they have this, and we don't. We don't have as much of it, right? They have one heck of a lot of it. If they started right now, they could potentially be putting $30 a month in to some sort of an account that is interest bearing, right? And in 90 years, they're going to be multimillionaires, right? Now, if I did that, I might be, $100,000, right? But that's it. Like the difference between $100,000 and multi-millions, right? But so I'm giving them a homework assignment to actually graph some of these exponential functions. But on the bottom of my homework assignment, I am reading a quote by Robert Kiyosaki, who wrote a book called Rich Dad Poor Dad. And his biological father, he just worked a steady job, and he was making like, whatever, $20 an hour or whatever. But then his mom, they got divorced at some point, and his mom remarried, and the man that he married was a millionaire, right? And so he was rich, right? So he had this interesting ability to sort of compare his biological dad to his adopted, or his stepdad, whatever it is. And so he was able to sort of compare, how does he think versus how does he think? What kind of investments does he do versus what kind of investments does he do, right? And so he started looking at that, and he wrote this quote. It says, the value of assets. Assets. What are assets? Yes.
Like resources that you can use, like mostly money.
Yeah. So technically, everything that you own is an asset, right? Your house is an asset. Your car, your bike, your phone, right? Your computer, your laptop, your iPod, right? They're all assets, right? Now, unfortunately, a lot of those assets depreciate. They get less valuable as time goes on, right? Don't you agree? I mean, you buy a cell phone, right? After a year, maybe 2 years, it's not worth very much, right? but when you first buy it, it's worth like 600, 800. They say it's worth like $800 to $1,000, right? It's ridiculous. But eventually, after 2 years, it's worth maybe $50, $100 if you're lucky, right? And so that's an asset. So ideally, the poor dad actually, as he watched and he saw his poor dad actually accumulated a lot of assets that over time became less valuable, right? But his rich dad created assets that eventually would grow more and more, and they would actually start to grow on their own. And it didn't make any difference whether rich dad was working or not, making $20 an hour at a job. That money that he invested, and he slowly put it on over time, over a long period of time, started to grow phenomenally to the point he became a millionaire. Poor dad kept buying more TVs and more iPods and more cell phones and more not that the rich guy didn't have those two, but you know what I mean. But he didn't understand the different types of assets and the value of time in those assets. So anyways, he wrote this quote. He said, "The value of assets often increases exponentially." Often, right? While the value of your labor, $20 an hour, that's a slope. That's a straight line. Your labor increases at a straight line, right? It doesn't increase exponentially. Your labor only increases incrementally, right? You might end up getting, at this point, you might end up getting a raise of, like $1 an hour or $2 an hour. So it's going to be slightly bigger, right? But look at the difference. You see what I'm saying? So this is poor dad. This is rich dad, right? So anyways, that's what we're sort of looking at. All those kind of things. Thanks, you guys.
Thank you.
So what I want you to do, the homework tonight, is basically to get some graph paper and actually practice graphing these. If you want, I'd like you to look them over, and if there are any ones you want me to do as examples before you tackle them, that's fine. I'm happy to do it. And I forgot to turn this off.